On the waves of sound, energy is moved.
A wave has areas of compressions.
Besides compressions, waves have rarefactions.
Sound needs a medium like air, water, or solids, like you and me, to vibrate.
As a mechanical, longitudinal wave, the oscillation of sound's particle movement is parallel to the wave's direction.
Acoustic variables are used to define the key characteristics of these very vibrations.
Amplitude reflects the sound's intensity or loudness, and it is also directly linked to a wave's energy.
Frequency, measured in hertz, determines the pitch of the sound.
And sound pressure is the force the wave exerts per unit over an area. Again, pressure is the result of force over a given area, measured in pascals.
You see, my friend, density is the concentration of mass within a given volume, expressed in kilograms per cubic meter. Mass is big, like qubit kinda big.
Lastly, distance measures how far a sound wave travels, using units like centimeters, feet, or miles.
Acoustic variables are the distinct properties that define sound waves.
These include sound pressure, measured in pascals, which represents the force exerted by the wave per unit area. Density indicates the mass concentration within a given volume, like kilograms per cubic centimeter.
Distance, in this context, refers to the displacement of particles caused by the sound wave, and is typically measured in units such as centimeters, feet, or miles.
In wave motion, the type of wave determines how particles in the medium move.
In transverse waves, particles displace perpendicular to the direction of wave propagation.
Keep in mind that, in longitudinal waves, particle oscillation occurs parallel to the wave's advancement.
Compressions in longitudinal waves are areas of increased density and pressure, while rarefactions are regions where both are reduced.
Question time. Okay.
Here's the first one.
You ready? What do you think is the role of a medium in the propagation of sound?
Answer: sound waves require a medium, like air, water, or solids, to travel because they are mechanical waves that transfer energy through the vibrations of particles in the medium. In a vacuum, where there are no particles to vibrate, sound cannot propagate.
Explanation: sound is a type of mechanical wave, meaning it needs a physical medium to carry its energy. The particles in the medium vibrate, creating areas of compression and rarefaction that move the wave forward.
Without a medium, these particle vibrations and, consequently, the sound wave cannot exist.
Question: how does amplitude relate to the characteristics of a sound wave?
Answer: the amplitude of a sound wave is linked to its intensity or loudness. It reflects the energy level of the wave. Higher amplitude means a louder sound.
Explanation: amplitude is a measure of the height of the wave's peaks. In sound waves, a higher amplitude indicates more energetic particle vibrations, which translates to a louder sound as perceived by the ear.
My dear protégé, you are making remarkable progress. Who knew physics would be something you would understand? You will work hard and your worth will enable you to move ahead. Here's the next question.
What distinguishes longitudinal waves from transverse waves in terms of particle movement?
Answer: in longitudinal waves, like sound waves, particles in the medium oscillate parallel to the direction of the wave's propagation. In contrast, in transverse waves, the particles move perpendicular to the direction of wave travel.
Explanation: the key difference lies in how the particles in the medium move. For longitudinal waves, particle movement is back and forth in the same direction as the wave, creating compressions and rarefactions. In transverse waves, particles move up and down or side to side at right angles to the wave's direction.
We've learned that sound is more than just what we hear. It's a wave of energy, traveling through various mediums, creating patterns of compressions and rarefactions. We've discovered the importance of acoustic variables like amplitude, frequency, and sound pressure, and how they influence our perception of sound.
So, stay curious, keep questioning, and prepare to embark on another exciting chapter of discovery.
Until then, let the sounds around you inspire a sense of wonder and anticipation for the wonders that await in the world of physics.
See you in Chapter 2.